Hello, I'm Kiara, a first-year PhD student at the Camborne School of Mines at the University of Exeter. My research aims to reassess the controls of magmatic-hydrothermal mineralisation and zonation associated around the Cornubian Batholith situated in southwest England. I'm going to pop out now, but you'll hear my voice throughout the rest of this presentation. This project is a collaboration between several mining companies, the National History Museum, and us at the Camborne School of Mines. Within this presentation, I shall firstly provide a brief explanation on the geological evolution of southwest England, after which I will explain our research aims and why this is a perfect time to conduct this project. Finally, I will wrap it all up with how my project is linked to a sustainable mining future within Cornwall. There are three main acts which occur during the evolution of southwest England, of which they can be divided into 10 scenes. This region has seen several mineralisation events, all related to regional fluid flow through rift-related faults. In this PhD, we are primarily interested in the granite-related mineralisation which occurred during the Permian. Firstly, there was a formation of a major ocean, which was then later closed during a continental-continental collision. This collision allowed for the heating of the lower crust, which aided in the crust's partial melting during the post-Furniscan extension. These events created major rift structures, which was then reactivated during later extensional events. Then, in the earlier Permian, extensional tectonics occurred due to the change in plate boundary motions over a large area of Pangaea. This event overprinted the earlier thrust-related movements and caused the onset of a basin formation and magnetism. The mantle-mafic melts were generated offshore and drove the massive crustal melting event which produced the extensive Cornubian Batholith over a period of 20 million years. Extensional faults intercepted and cut through these granites as rifting occurred throughout their emplacement. These granite intrusions are around 8 kilometers thick and composed of several different granite types, as shown within this picture, which occurred due to several rifting episodes allowing for several pulses of granite magnetism to accumulate. The different granite types are also theorized to control the composition of ore fluids which flowed through the rift faults created during the same event, and ultimately formed this world-class mineral vein deposit of tin, tungsten, and copper. These granite-related deposits have been mined historically and are being reconsidered for future mining endeavours, and they are also the main focus of my PhD, but we'll touch on this more later. The rest of the second act is defined through 3 rifting events, all with different orientations. We, however, are interested in the first rifting event due to its creation in the fluid pathways for basinal brines from overlying sediments to flow through and create the cross-course deposits containing lead, zinc, and silver. As in the name, these deposits cross-cut the earlier granite-related mineralized veins, and in areas of interception, we see a sharp increase in the vein's grade and tonnage. Now, this is most of what we can see on the onshore geological history, due to the erosion of several other rifting and depositional events. Within the Cretaceous, we do see fluids from these sedimentary basins migrate through reactivated rift structures to create hydrocarbons, as well as our 5-element group with uranium deposits. The last act is the formation of the Atlantic Ocean, which now brings us up to modern day and completes the geological history of southwest England. So now that we have covered the background information, let's dive into my PhD and the need for it. During this project, we will integrate historical mine data and core logging with laboratory techniques investigating mineral analysis, as well as melt and fluid inclusion analysis through a laser abrasion technique. This is key data that we will use to re-evaluate the mineral deposits of southwest England, focusing on some key areas, which are as followed. As you will hopefully remember from my geological history, the Cornubian Batholith was formed through several pulses of magma leading to their varying granite composition. As the granite is the source of the fluid, different compositions may affect the exsolved fluids and subsequently create different ore assemblages in our mineralized veins. Therefore, we not only want to determine the compositional variability of these fluids, but also link them to their granitic source. This has yet to be done in the southwest England and will be achieved using melt inclusions from samples extracted from deep geothermal sites in depths of 5 kilometres. We can also provide an insight into the variation of ore assemblages and mineral relationships within different deposit types, while putting this into context with fluid mixing and migrational structures to further understand the controls on the mineral precipitation. Like the point I stated earlier, how the interaction between granite-related mineralization and cross-course causes a sharp increase in grade, understanding this formation will be useful in mineral exploration campaigns and the companies that we're working with. Another aspect that we will research is the metal zonation which occurs around the granite batholith, with tin and tungsten seen proximal or within the granite itself, and then copper, zinc and lead are dominating distal regions as shown within this graph. Why this metal distribution is occurring is poorly understood. This research will provide an insight in the complex relationships occurring between volatile phases, faulting and fluid mixing, which all took place to develop this world-class ores deposit. Lastly, we aim to unravel the caramel copper conspiracy. As I've stated, these granites were formed by crystal melting, which means they are a paraluminized oxide system. This system results in tin and tungsten being incompatible and partitioning into exsolved fluids. However, copper is compatible and therefore should not exsolve into fluids and instead be incorporated into mineral structure. Therefore, the occurrence of copper in the deposits indicates another aspect at play. Could the copper be originating from a mafic system at depth, where the opposite is true? This allows copper to escape the system and be transported to higher levels in possibly sulfide blebs or in fluids. This is a recently proposed theory for copper-rich tin deposits, but require more information on ore assemblages and fluid composition to have a full understanding on what is occurring within southwest England. Those were the primary research goals of my PhD. But why conduct this project now? And what is our link to sustainability? Well, this PhD is needed now because there's been a substantial hiatus in research on the region's lode systems following the end of deep tin mining in 1998, which is when I was born. However, with the resurgence of exploration drilling and deep geothermal energy, it has provided a timely opportunity to reassess the mineralization processes which are occurring using modern-day analytical techniques. Through undertaking this research, we're not only solving large-scale questions on pyrogenesis, but also aiding our collaborating companies with understanding their deposits and ore relationships, heightening their exploration campaigns. This means that when mining does occur, extraction of only the material that is required, and minimizing waste and energy during the process. The metals that we are investigating, particularly copper and 5 elements, are essential for all our electronic devices and our transition to a sustainable renewable energy source. This will aid us in meeting climate change goals which are crucial for our future. Hello again. Thank you so much for listening to my PhD, and a big thank you to NXGEN Resources for providing me this opportunity to speak with all of you and for organising this event. Thank you for listening. Bye for now.